Thank you, Mr. Feynman. I start with the aim and objective for square plate without crack. This is practical research, not mathematical research. And we want to analyze what the maximum critical compressive stress we can apply of the insert. It is a cutting tool from tungsten carbide with cobalt. We use it in milling, in turning, and other process machining. So for unique and known the diameter D of the plates. And we want to finding the optimal hole diameter that located on the center of the hole, the plate, W, to obtain stability in the progress of the future crack and that no fracture occurs. So we, in compressive, apply the load in the external load in the top face of the square plate. So we know that the symmetrical of the geometrical and the loading, we have the vertical line is symmetrical planes, and also the horizontal plane is a symmetrical plane. So there is no shear stress on these symmetrical planes, and there is no deflection perpendicular to the face of the plane symmetrical. So here we get tension, and the upper load we get compression. So you have to transfer from tension to compression in normal stress, because there is no shear on the vertical and the horizontal plane symmetrical. So the normal stress is the principal stress, okay? And we can get the stress intensity factor K1 is maybe smaller because there is tendency for stability in crack propagation to the existence of compression stress along the line, the GE, the length GE of the plate. So the tungsten carbide, they have a lot of advantage, the high resistance, high hardness, high thermal resistance, melting point, and we examine the plate with 6% of cobalt and 24% of tungsten carbide. The cobalt is between 6 to 15 or 20% maybe. So from process plasticity, they take more cobalt, that it will be more ductility. So the objective function is to minimize the goal maximum normal stress occurring on the vertical and symmetrical planes. We want to get a compact square plate with minimal dimension as possible, so that it's the cheapest for given hole diameter D, if you know it. We can perform different experimental to evaluate the fracture toughness of the brittle materials. So you're using a cheap and compact square specimen, and we can evaluate a reliable value K1C under compression loads. So the first criterion was the strength. So it's a brittle material, so there is no yielding point, and the ultimate tensile strength is less than ultimate compression strength. This is the value for this materials, brittle materials. And we know that this is the profile of the normal stress along the vertical symmetrical line CE. So the maximum principal strength is in the point C, and the maximum minimum normal stress in the compression is in point A. So we can know the factor of safety for compression and factor of safety for tension. So what is the main problem in this square plate without cracks? There is no analytical solution. We have analytical solution of the infinite plates with central hole from Kirsch solution. So we want to find the dimension and calculate of the real stresses, their distribution in the vertical line CE and horizontal line under constant displacement or constant pressure. So the solution using finite element, essential numerical tool for handling such problem with reduced degree of complexity. So this is the solution for infinite plate, because the surface of the hole, there is no stresses, tangible stress or shear stress, radial stress or shear stress. We have only tangible stress. So we get the stress intensity factor is 3 for infinite plate. We know that. So what we performing a numerical solution to achieve the objective. So I developed numerical using optimize the ratio dW, where D is the hole diameter and W is the size of the square plate. We take a different ratio between 0.1 to 0.71 in terms of fracture strength for heterogeneous brittle materials under uniaxial compression and uniaxial displacement. So what is the general procedure to performing simulation using finite element analysis? This is practical research from Yifrach company, is one of the leader of the company for cutting tool in the world. I make a solid model for the insert. I make a mesh for all the plate. I make boundary condition, and I get the results. Is just example here in the line. The maximum we see is the point C, and in the minimum is the point A. So this is example for D over W is 0.39. The model without crack, I make it static analysis with ANSYS. 3-dimensional solid element analyzed. We take XI with 20 nodes, brick elements, and triangular with 15 nodes. The finite element mesh in idealization was finer with a high stress gradient near the hole, and coarser at the out of the no stress gradient. So we see here a quarter of a model, because we have symmetrical in the loading and geometrical and boundary condition. This is example, just example one, to calculate in a quarter model between what's going on?
To go back, or
What?
you need to go back
Yes. Here?
here, yeah.
Okay, thank you. So we make a quarter model, and we get the same results like the whole model, So I know that the mesh is okay and the solution is okay. What we see here, it's just the simulation subject to uniform uniaxial displacement for different d over w from 0.1 to 0.71. As we can see, I can take the length CE like as a lever. Okay, when the maximum normal stress develops at the point C, where the R over R, little r to capital R is 1, and the ratio d, the over smaller, is for a constant plate. The length CE will be greater, therefore, we'll get greater maximum potential normal stress at point C, and vice versa. Since the plate made from brittle materials that is sensitivity to tensile stress, that the future crack will begin to develop from point C because there is a maximum tensile stress, and we know that the stress, the fracture, the future fracture will be start from point C along the line CE with mod 1 fraction. So we see the stresses along the horizontal symmetrical line AB, and we see that as the ratio d over w is smaller for constant plate YW, and the length AB will be greater, therefore, we'll get maximum compressive normal stress at the point A, and vice versa. So, resultant conclusion for square without cracks. We knowing the high concentration is located around the hole, of practical important designer engineering circle to achieve minimum stress concentration factor. From the analysis of the optimization criteria, it was obtained that the optimal ratio d over w of the square plate is obtained from the ratio d over w is equal to 0.39. Future cracks in the square plate with the central hole will occur always in the maximum normal stress at the vertical edge in the point C under uniaxial compression loads. And the future crack will always progress in the direction of the external load applied. As we see that the plate, it's bending inside when we apply the external load, and the fracture is in mode 1. So after we know what is the optimal of the size of the hole, we get the analysis in for square plate with cracks. So we are interested in understanding the propagation of the crack emanating from the center circle hole in square plate under compression, as we see here. 7 cracks lengths modeled numerically from A is 0.5 until 3.5 millimeters. Under pressure, 705 megapascal, and displacement minus 25.689 micrometer. In cracks, I use the Abacus CE 2020 commercial software with general static implicit, and analysis were conducted. So the undeformed geometry is shown in Fig 1A. This is the optimal that we get from no cracks. Because the symmetrical, we make 1/8 of the geometry was analyzed materials is shown in Fig 1B. So the mesh, the model with different cracks, the numerical mesh for the crack belong 0.5 to 2.5 consists 53,408 800 elements, quadratic hexagonal, C3D20 in Abacus. The seed size was 125 micrometer. And this is for the short cracks. And this is for the crack. For the mesh was made locally denser near the crack tips, as shown in Fig 2b. And all mesh were checked for numerical conversion. So this is definition of the crack. So this is the boundary condition. I have a symmetrical, 3 planes of symmetrical. We use the displacement extrapolation method in introduction. The thickness of the plate minimum is very small in brittle materials. This is the criterion. If I can make plane strain on plane stress, it's this criterion met for most brittle materials. So is the plane strain condition. We use the normal gap at the mid plane where the plane strain condition prevail, are fitted 3 terms of the asymptotic expansion. And from the literature, the normal gaps may be approximated by the set of this. This is delta U1 is the equation where U1 is the crack opening displacement. By selecting any set of 3 points of the edge crack in the distance from the crack tip, a set of 3 linear equations assembled to the coefficients A0, A1, and A2 are calculated. I make a code MATLAB for this, and this is the value for K1 for plane stress. And what we do, we applied for different, for a quarter of model along the line CE. We make the pressure 705 megapascal and the displacement. And what we see here is the point where we can, until crack of 3.3 millimeters, that it could be stable. Okay, I make normalized parameters, and this what we see. We see that for A greater than 2 millimeters, which means the crack advance might stop, depends on this we get. And as we see in both curves, we see regions where the slope is negative, hence the crack may be not propagate. It is the pressure that gives reduction in K1, where there is no crack. The ratio between load and the fracture toughness, K1C, will dictate the crack advance. And for the example, if the load Qs for K1 reach to K1C is applied, then the crack in the stress load will propagate much longer than the crack under displacement loading. And the results, the main difficulty to produce natural crack in very brittle materials such tungsten carbide under conventional tension or bending load experiments, according to ASTM E399. I prefer the solution to perform different experiment with using a shaped component specimen, easy to perform, and for evaluating the reliable of the K1C experiment. So what we can do at the maximum normal tensile stress always develop the upper and the lower points along the free edge of the hole. At this point, artificial vertical cracks were made using by EDM method. This vertical crack is used to induce local tension stress, and this leads to fracture but by mode 1, and we can evaluate fracture toughness K1C. As we see here, this results and for stable propagation.
Thanks to the speaker.
Thanks you for your attention.